stuff. So what about something like this now? Again, this is just practicing sigma notation. So you got to write that as a sum, as a discrete sum. Yep. Good. 5 terms. Starting at 1, going to 5. Let's say it again. 1 over. 1 divided by 2 to the k. There you go. Does that make sense? Okay. Give me thumbs. How we doing? Is that good? Okay. All right. So then, okay, write that in sigma notation. This is one more. This one's a little tricky. What seems tricky about that one? Yeah, that's alternating signs. Can you think of a mechanism for doing that? Can you think of a way of changing the signs of each term? Any ideas? Any ideas, Madeline?
Well, an idea for like the signs changing isn't if you take like an odd number or a negative number to an odd power.
Okay, good. And what if I want to have a part of this that's only controlling the coefficient then? What odd number would I take to a power? -1, yeah, there you go, good. So I'm going to have a negative, so to get to start negative and then go positive, I'm going to have to start with some odd power of -1, but it's going to have to alternate with each term, isn't it? Okay, good. All right, what else? There are multiple ways you could do this. Like, for example, I'll illustrate what I mean here. Like, what if we chose to write this as the sum as I, they always use k, I like to use I. What if I starts at 1? How would I do it? How many terms would I have, first of all? 5, okay. Well, so there is a way that you can, there is a way you can come up with formulas of more complicated ones by writing a recursive formula, by writing a term in terms of the previous one and then solving. I don't think I'm going to spend a bunch of time on that, though. That's typically not something you do in high school. I mean, maybe if there's time, we'll come back and do a couple of those at the end. I just don't want to eat up too much time on this. Okay, so we're going to say to the I this time, though. I used I as my index variable instead of k. It doesn't matter which one you use. So we've got -1 to the I. Good. And that's going to work, isn't it? Because it's going to start off being odd. Now, what if the signs had been switched? What if the first term was positive and the second term was negative? What would you do then? You'd have to start off with an even power, right? So what could you do to that exponent to make it even? Well, if I do 2i, it's always going to be even. I need it to start even and then go odd. Say it again. Yeah, there you go, +1, exactly. We could have just done to the I +1, right? And then it would start off with a power of 2, but then it'd go to a power of 3. It doesn't really matter with -1. It doesn't matter which odd or even power it is. Every even power is the same. It's 1. Every odd power is -1. Good. Okay, now what about the other parts of this then, though? How am I going to start with 1/6 and just incrementally work up by 1 on the bottom. What am I going to have to multiply that by? Yeah, does that make sense? Very good with that? Good. Okay, I could have alternately, I guess I could have done something like this, just to make a point here. I could have done the sum as I go, we'll make it k this time, so it's different from the top one. So k starts at 6 and goes to what then? What would it have to be if I'm starting the index variable at 6?
Oh, just like the new thing.
What would the top have to be? What number has to go there? If I'm starting with the 6th term. Like here I started at 1 and I counted from 1 to 5. Here I'm starting at the 6th term and counting to what term? 10th, yeah. Okay, and then I'd have to have -1 to the what?
So is that top number the number like that you go in total or the number that you start from?
It's the number you go total. So the way it's written right now, this is the first. If we're just, that's the index variable. It's just keeping track of each term. So we're starting with I equals 1, so that's I equals 1 is right there. I equals 2, that's the 2nd term. There's the 5th term, right? If I did it this way in red, this one would start off with, we're starting with term number 6, and we're ending with term number 10. Each term just gets like a label. Does that make sense? Okay. So when you're doing a summation, the variable of summation is the index variable. It's just the one that's stepping incrementally from this one up to that one. So you're always going to know that, like in this case, 5 minus 1, this number minus this number plus 1 is always the number of terms, right? So in this case, it'd be 10 minus 6 is 4 plus 1, so there's 5 terms. If I started with the 99th, or if I started with the 100th, then I'd have to go to the 104th, right? See what I'm saying? So then what would that accounts, we have to count for the sign though. So it starts negative. If my first term is 6, what would the power of -1 have to be? Yeah, something like k minus 1 or k plus 1, right? Okay. And then how am I going to get, well, then the other part gets easier though, because now what's this is going to be? If I want to be able to produce this sum, 1 over k, yeah. There you go, right? So those are equal. I mean, those mean the same thing, just different ways of saying it, okay? Depending on where you're starting which starting index variable you're using, starting value of the index variable. Okay. So what about stuff like this? Now this is just making the point that sums are linearly independent, so they can be added or subtracted, and they're also you can multiply sums by scalars. You can multiply them by a constant, and just treat the sum independently. So for example, like if they're telling us that the sum of a sub k, as k goes from 1 to n, is 5. We don't know what the terms are. We don't know how many they are, but they're just telling us that sum is equal to 5. The sum of b sub k, as k goes from 1 to n, is 12. Again, we don't know how many terms there are or what the individual terms look like. We just know what the value of the sum is, right? Then what is that? What's the sum of 5 times a to the k as k goes from 1 to n? 25, right? How come? because we're able to, and this is kind of the important thing, but this should be very natural because this is what we've been able to do with limits and derivatives and antiderivatives. We could rewrite that as 5 times the sum. Does that make sense? We can just pull the 5 out front, okay? So we end up with 25. How about this one? What's that one going to be? Everybody show me fingers. What's that one going to be? Yeah, it's just 1, isn't it? And then here I'm just going to get 17, aren't I? Right? And here I'm going to get -7. And here I'm going to get, I mean, you got the idea, 12 minus 35, whatever that is, right? Okay? No big deal, okay? Do you see why this would work too? Like, if let me go back to the previous example. What if I had something like this? Like, what if I were to, I'm going to show you how to do this too, how to add this up. Okay, so that's kind of a pain to add up all those fractions, isn't it? Right? Okay, but we can use, we can add up sums pretty easily using our TI-84. I'm going to show you TI-84 because that's what you can use on the AP test. You know, if you were going to do the AP test, I hate to say this, but I honestly think it's to your advantage to have the new TI. It's the new operating system, the TI-84 Plus, the color edition. The menus are just better. I mean, like the way you get to apps and stuff, it's way more intuitive. Like, I'll give you an example. If you go to, we'd go math, and then I'm just going to go up from the bottom of that list, and look, there's summation. It's the 10th option, right? Look what that looks like. I mean, how simple is that, right? I mean, whereas if you try doing it on one of the old school TI-84s, and it doesn't look so good. Does yours look the same way? Oh, it does? Oh, okay, never mind then. Oh, but it's not I got you, okay. Okay, it's just not the color edition. Okay, so all you got to do here then, I mean, this is exactly as simple as it looks. We've already got here what this should look like, so let's use the blue version. For your index variable, you know, you're kind of limited. You're always using the variable x, right? If I push the variable key, I'm just starting, but that's okay, right? X is just my variable of summation, no big deal. So we're going from, I wonder if you can use, I just want to mess around for a second. What if we tried making that an I or a K? I kind of doubt you can, but I'm going to try this. I'm going to go alpha K as K goes from 1 to 5. And then we're going to try this. We'll try this here. So I've got it. Now, I'm going to have to put everything that's being summed inside those parentheses. So I'm going to have some nested parentheses. I'm going to have a -1 to the K, so alpha K, times one divided by K plus 5. And then I have to have my other parentheses out there to close the whole thing. Okay, let's just see if that works. I kind of doubt it's going to if I use a variable like just an alpha variable. No, I didn't like it. Oh, you know what? Actually, it was just I had one extra. Let's try that. Oh, it did it. How about that? So you can. That's kind of cool. You can. I mean, I don't know what the motivation for doing that would be, but you can. You'd probably just want to use X instead of K. I'm just curious here now, what if I put an X in there, if it would leave? I don't think it's going to, like the TI-89s or the, what are they called, the TI Inspires, is that what they're called? Would do this symbolically, but if I try to put an X in there with the K, I just want to see if it preserves that X. I don't think it will. No, it doesn't do it. Doesn't do it. It just assumes whatever value is stored currently in X, it's going to use. So there's no reason for you not to ever just use X's on this. It's fewer button pushes, just use X's. Okay, on Desmos, I'll show you Desmos, but you really should be using the TI-84s. Although this is kind of, I mean, just this is nice to know how to do. If you go to the graphing and you want to do a sum, how the heck, I think you have to go down here. Let's try this. Functions. There it is right there, calculus. So you can do a sum. Oh, that's pretty cool. It picks n for you, that's all right. As n goes from 1. Oh, you're not seeing that, are you? There you go. So where I found this, if you just go down to the keyboard at the bottom and you go to functions and you just go down to the calculus, you get integrals and all kinds of stuff down there, okay? I wonder if I type sigma. No, it doesn't do it. Okay. So we're going from 1 to 5 of negative 1 to the n times n plus 5. Okay, did that give me the same answer? Did not. Why is that? Oh. Oh, yeah, it did. Yeah, it did. Look, it did. That top one was the correct answer. The bottom one, I must have had a different value stored for X. It must have been, for some reason, it must have been stored as like 10 or something. I'm just going to clear those out. Oh, I did that again. There, same answer, right? Same answer either way, okay? So there's a quick way for us to add up these sums. Okay, so next one then, when you're trying to add up sums, there are some discrete sums that we add up so frequently that we have formulas for these. Now, if we had a little more time, there's kind of a cool way you can come up with, by using what you're talking about, Andy, by using induction, math induction, you can come up with these formulas. If we had a little more time, I'd kind of take you through that, but it's really not that big a deal. So I'm just going to give them to you. When you add up, if you add up a constant over some, as I goes from 1 to n, or k goes from 1 to n, doesn't matter which variable you use, then the result is, of that sum, it's always just the constant times n, which makes sense, doesn't it? Because really, what would this sum look like? The sum of c as I goes from 1 to n, well, that's just n terms that are all equal to c that we're adding up, right? So c plus c plus c plus c, n times, that's the definition of n times c, right? So that's all that is. From there on out, it gets a little more complicated. So the sum of I as I goes from 1 to n, and you could be k's instead of i's, is just n times the quantity n plus 1 over 2. That's just a summation formula we have. The sum of I squared from 1 to n is just n times n plus 1 times the quantity 2n plus 1 over 6. And then I cubed is just this bottom one. Sum of I cubed is just n squared times the quantity n plus 1 squared over 4. So you can always just directly use those formulas. And honestly, that's probably almost quicker than using a calculator. Because you can, like this first one, What's the first one going to be? You don't even have to really think about it. What's the answer to part A? Sum of K. What is it? 17K. Right? Okay, how about the next one? How about B? Okay, well, we're just going to use, I mean, we could put that in a calculator, but we could also just use this. Oops, not that one. This one. Just use that summation formula, right? So the sum of K squared from 1 to 17, this is just going to equal N, or K in this case, right? This uses N's, this uses K's. 17 times 18 times 35, right? Divided by 6. See how I got those? Okay. And then 18 over 6 is just 3. So we'd get 17 times 3 times 35, whatever number that is. That's our answer. Okay? Make sense? This third one, we're just going to use that formula. So we're just going to get 17 squared times 18 squared over 4. That's our answer. Okay? All right, so on to, so the first assignment is about nothing other than just practicing sigma notation. That's all it is. All right, so now we're going to start to take a look at how we could add up areas under these curves, right? Well, the way we could go about doing this is we could divide up the area into subintervals and just approximate each of those subintervals with some kind of easy shape, like a rectangle, right? So if we're going from 1 to 4, well, what if we, for example, just broke this up into 12 subintervals to try to get a fairly decent approximation, right? So we'll let n equal 12. And what would the width be then of the subintervals? If x is running from 1 to 4 and we're dividing it into 12 subintervals. What would it be? Not a third. Close. Remember, it's starting at 1. It's not starting at 0. It's going from 1 to 4. Fourth, right? And how do we get that? Well, delta x would be easy to calculate here, wouldn't it? Delta x is just going to equal the width of the entire interval, which would just be 4 minus 1, right? Does that make sense? The ending value of the area, ending x value, minus the starting value, divided by the number of subintervals. That's how I'm getting my 1/4. So there's the width of each interval. And so then we could label these things. We could label these sections. Like this first one that starts at 1 and ends at 1 1/4 would be subinterval 1. This is subinterval 2. That's subinterval 3. And some random one out here in the middle is just going to be the ith subinterval, right? And we're just going to count these things up as I goes from 1 to 12. Now the idea here is if we could come up with some area formula, this would be ideal, right? If we could come up with some area formula for, let's say, something like the inscribed or circumscribed rectangle, right? And we'll look at some different ways to do this. But if I could tie the area of these rectangles to only the value of the index variable, then I could add up this area using sigma notation. You see what I'm getting at? We'd like to be able to define the area of the ith subinterval as a function of I. Okay? That's our goal. So let's start off here. Let's use we're going to use a right sum, meaning we're going to use the right edge of each subinterval to define the heights of the rectangles. Because this is a monotonic increasing function, that means these are all going to be overestimates. Okay, this is going to be, this is two things at once. It's a right sum. I'm going to write this down too. So we'd call this a right sum. Because the rectangle heights are defined by the value of x at the right edge of each subinterval. Okay, does that make sense? Okay, that's really important. So it's a right sum because the rectangle heights that are defining the areas of the individual rectangles are tied to the value of the function at the right edge of each subinterval. Everybody see how that works, right? So these are the points wherever, like the right edge of the first subinterval is there. So that's defining the height of the first rectangle. The second subinterval, there's the right edge of the second subinterval. That's defining the height of the rectangle. Okay, so this happens to also be then what's called an upper sum because these are all circumscribed rectangles. They're rectangles that are always going to overestimate the area a little bit, right? Now, if the function were a decreasing function, it'd be the opposite then, right? The right edge would be the lowest edge of each subinterval, and they'd be an underestimate, okay? So because of that, we also call this an upper sum. But I'm going to say the upper sum is incidental. That's not as useful to think about things in terms of upper sums and lower sums. Whoops. Oh my gosh, come on. There we go. It's also an upper sum, but we don't really care about that, right? The upper sum is sort of incidental. And you're going to see why that is in a little bit. When we start adding these things up and we're taking a limit as the number of rectangles gets really big, it doesn't really matter if it's an upper sum or a lower sum. The limits are going to converge anyway. So we'll just always pick the most convenient sum we can to add up the area because ultimately we're going to extinguish all that overestimated or underestimated area anyway. Now, a different approach might be if we were really going to rely on some numerical estimate and we weren't going to be able to take a limit and have this thing become infinitely accurate, get a perfect evaluation of the area, then we might need to do something like, okay, well, let's calculate an upper sum and a lower sum and average the two or something to get closer to an exact value. Or I might pick like a random distribution in here. There's another kind of novel approach that people take sometimes when you're trying to find algorithms for quickly evaluating things. You might take a random distribution that's going to completely randomly decide is it upper or lower for each subinterval. And if you have a sufficiently large number of subintervals, that's going to work out statistically to be 50-50, right? So some other approaches, and that's a whole different part of math when you're talking about like doing numerical analysis. And we're going to come back and touch on this again because it turns out there are some functions that are not integrable, that you can't find an antiderivative of them. One does not exist mathematically, which is really bizarre. For example, like the sine of, what would be one that would work? Like the sine of x squared. There is no integral of the sine of x squared. There isn't an antiderivative that exists. You can't differentiate a function and get sine squared as a result. So for those, we are going to have to go back and use some kind of a numerical approach. But what we're going to do with it, we're going to pick something different. For our numerical approach, rather than having to try to find some average of upper and lower sums, we're going to use a different shape. We're going to use trapezoids instead of rectangles. We'll pick trapezoids that are defined. The left edge of the trapezoid, the left height of the trapezoid is defined by the height at the left edge of the subinterval, and the right edge defines the right height. And so the trapezoid would just look something like this. And those are going to match the curve better as the number of trapezoids gets big, right? You get a much more accurate estimate. But in places where we don't get an exact, where we can't take a limit as n approaches infinity, it's impossible to do, we'll have to do something like that. But that's in the future. Okay, okay, this is what a left sum would look like for that one. Everybody see that? Okay. Where we're just defining the heights of the rectangles by the left edge of each subinterval. We're going to see that the math makes a right sum just a little bit easier to calculate than a left sum. When you do the sigma, you do the discrete math using sigma notation, this is a little more cumbersome, and you'll see why. So we really don't ever do these. We just always use right sums. You can compare the two. And you can see that they would kind of bracket the answer there if you average those two, right? Okay. All right, so let's do some calculations then. Like, let's actually go through the process of finding an upper sum and estimating what that would be. Okay, this is something that you always, I don't know, I guess there's some value in this, but every calculus textbook in the world has you do this, a couple examples of this, where you're going to find upper sums and lower sums and then, you know, average the two. And I'm not sure why it's such a big deal, but I think there could be some open-ended questions on the AP test. That could be one where you have to do something like that. It's not hard to do. Literally, it's just adding up areas. That's all it is. If we wanted to find this one where n equals 12, we've just got to go through and find, okay, what's the height of the function there times the width is always 1/4, right? The height of the function, so the value of the function there times 1/4 plus the value of the function there times 1/4, and add all those up. And then that's going to give us the total area. So, I set this up like last year or the year before on a Desmos document. It's not hard to do. I mean, the area, what did I do here? I think I set up an area function that was just whatever the width is times f of x sub 1. And then x sub 1 just tells me you can always turn what the value of the index variable is into an x value, right? That's easy to do. Let's see how we could do that. Like, how could I know, like, how could I find out that how could a formula predict, let me say it differently, how could a formula predict that when I equals 3, that's going to be the value of x that I'm plugging into the function. Okay? So what we're really trying to do here is we're trying to come up with something like, instead of saying, I want to come up with something I'm going to call x sub I. So for the ith term, that's going to be the value of x where I evaluate the function. Okay? This is actually pretty easy to do. Think about what we're asking here. We're saying delta x is the width of each subinterval, right? So that's akin to the length of a stride as I'm walking forward. What I really want to be able to do is take 12 strides and cover the entire area from 1 to 4, right? So we know that the width then, my strides are 1/4. So if I want to know the x value wherever I end up after so many strides, aren't I just, the amount of distance I'm walking from the beginning is just going to be the number of strides I take, which is going to be I, or k, whatever you want to call it, times delta x, isn't it? So when I've taken 3 steps, I've gone 3 times 1/4, so I've just walked a distance of 3/4 from my starting point. Well, my starting point we'll always define as a. That's what I mean, in our case it's 1, but we call a the starting value of my area, right? So x sub I is really simple. It's just going to be wherever the area is starting to be reckoned. That's why we use that word in calculus. We reckon area. Sounds kind of good for Eastern Oregon. So a plus I times delta x. That's always going to give us, that predicts the value of the function at the right edge of the ith subinterval, doesn't it? Right? So we would just say a is equivalent to x sub 0. That would be x sub 1. That would be x sub 2. That would be x sub 3, etc. Right? And so if I wanted to calculate the value of the function there, that's just going to be f of x sub I. It's just going to be f of whatever this gives me for my particular case, right? In this case, a is 1 and delta x is 1/4. So I'm just getting f of 1 plus 3 times 1/4. 1 plus 3/4, that's 7/4, right? Everybody see what I'm doing? Give me 1 to 5 on that. Is that making sense? Okay. We'll hit that again tomorrow. But then if I wanted to calculate an area of this thing, so how did I, when I created this spreadsheet, how did I get these numbers? Well, isn't that just what we could call a sub I? The area of the ith subinterval? The area of the ith subinterval is just the height of the rectangle, which is just f of x sub I, times the width, which is delta x, right? Okay, does that make sense? So we'll hit this again tomorrow. I mean, I know that's a lot of information in a real short period of time, but this is what we're going to end up doing when we start to add up these areas, is we're going to take a limit of this eventually as n goes to infinity. And what's going to happen to the width of the subinterval as the number of subintervals goes to infinity? It's going to shrink down to 0, isn't it? Approach 0, yeah.